In August 2024, a research team at Northwestern University published a scientific paper that quietly challenged one of the biggest assumptions in modern construction. Instead of inventing a new chemical compound or designing a synthetic building material, the researchers used something extremely simple: ordinary beach sand. They saturated the sand with seawater and applied a very small electrical current between 2 and 4 volts, less power than a single AA battery. Within minutes, something remarkable happened. The loose grains of sand began to fuse together and transform into a rock-hard solid mass. No cement was added, no chemical binders were mixed, and no massive industrial kilns were used to heat limestone to 1400 degrees Celsius like traditional cement production requires. The entire transformation happened using nothing more than electricity, sand, and seawater. Professor Alessandro Rota Loria, who led the research, described the first laboratory experiment as a moment that felt almost impossible to believe. The sand did not simply become compacted. It transformed into a dense, cohesive structure that behaved like natural stone. It looked like rock, carried load like rock, and structurally acted like rock. The reason is simple. Chemically, that is exactly what it was. The material was not manufactured or fabricated in a factory. It was grown directly from the minerals already dissolved inside seawater. The research paper was published in Communications, Earth, and Environment, a respected scientific journal in the Nature research portfolio. It was peer-reviewed, examined by independent experts, and confirmed by mineralogists. The science was solid. Yet after publication, the discovery quietly disappeared into academic archives, while the rest of the world continued buying bags of Portland cement for $30 each, without realizing that a completely different approach to construction might already exist. The question this raises is simple, but important. When a discovery this significant appears in one of the world's most respected scientific journals, why does almost nobody working in construction know about it? The answer requires going back long before 2024. It begins in 1976 with a German-born architect named Wolf Hilbertz standing underwater near the Texas coast. Hilbertz was not a chemist. He was trained in architecture, which may explain why he approached the problem from a completely different perspective. He became fascinated by coral reefs. A coral reef is structurally stronger than many commercial concrete materials. It grows in harsh saltwater environments, repairs itself when damaged, and becomes stronger over time. Most importantly, coral reefs build themselves from nothing more than seawater and natural biological energy. Hilbertz asked a simple question. What if the biological organism was not necessary? What if the same chemical process could be recreated artificially using electricity? To test the idea, he placed 2 metal electrodes into seawater and connected them to a low-voltage power source. As the current flowed, something unexpected happened. Minerals dissolved in the seawater, including calcium carbonate and magnesium compounds, began to precipitate and attach themselves to the metal frame. Layer by layer, crystal by crystal, a dense mineral structure slowly formed. It was essentially rock growing directly out of seawater. Hilbertz called the process mineral accretion, and the technology eventually became known as Biorock. By 1979, he had published his findings in the IEE Journal of Oceanic Engineering, and in 1981, the United States Patent Office granted him a patent for large-scale structural mineral accretion. The material created through this process had compressive strengths between 3,200 and 5,650 pounds per square inch, comparable to the strength of concrete used in sidewalks and smaller building foundations. Structures could be shaped into almost any form using metal frames as guides, and the electrical current required to grow them could even be powered by solar panels floating on the water surface. Most importantly, the process required no mining, no limestone extraction, no high-temperature combustion, and no large industrial factories. Hilbertz spent the rest of his life developing the idea. Over the years, he worked with scientists and engineers to build artificial reefs in more than 40 countries. More than 500 Biorock structures were eventually constructed around the world. His work was displayed at the Museum of Modern Art in New York and gained attention in marine science communities. Despite the scientific recognition, the construction industry largely ignored the technology for decades. To understand why that matters, it helps to look at the scale of today's cement industry. The global cement market exceeded $47 billion in 2024, and the broader concrete and construction materials sector is valued at more than $1.8 trillion worldwide. Humanity now pours more concrete every 3 years than was poured during the entire 20th century. China alone used more cement between 2011 and 2013 than the United States consumed during the entire 1900s. But this enormous industry carries a major environmental cost. Cement production is responsible for about 8% of global carbon dioxide emissions each year. Producing a single ton of cement releases around 900 kilograms of CO2 into the atmosphere. The reason is chemical. Portland cement is created by heating limestone at extremely high temperatures, and that process releases carbon dioxide as a natural byproduct of the reaction. Even the most advanced factories cannot eliminate this emission entirely because it is built into the chemistry itself. While companies are experimenting with carbon capture systems and alternative additives, these solutions still require expensive infrastructure and do not fundamentally change the process that has been used since the 19th century. The Northwestern research team examined their electrical method and calculated the potential cost difference. Strengthening 1 cubic meter of marine sand using electrodeposition could cost roughly $3 to $6. Conventional binders used in similar coastal construction projects can cost up to $70 for the same volume. Instead of mining raw materials, transporting them to factories, burning fuel to process them, and shipping cement around the world, the electrical method simply uses electrons and the minerals already dissolved in seawater. The chemistry behind this process is surprisingly elegant. Seawater contains large amounts of dissolved ions, including calcium, magnesium, and bicarbonate. These are the same building blocks that coral reefs and shellfish use to create their skeletons and shells. When a mild electrical current flows between two electrodes submerged in seawater, the chemical conditions near the negative electrode change. The pH level increases, causing calcium carbonate to lose its ability to remain dissolved in the water. It begins forming solid crystals that attach themselves to nearby surfaces and sand grains. Over time, those crystals grow bridges between the grains of sand, locking them together into a solid stone-like structure. Researchers also discovered that the process is reversible. If the polarity of the electrodes is reversed, the chemical conditions change again, and the mineral structure slowly dissolves back into the water. The solid rock returns to loose sand. That means structures created using this technique could theoretically be modified, repaired, or removed without heavy demolition equipment and without producing massive amounts of construction waste. At the same time, another area of research has explored a similar concept using biology rather than electricity. Scientists studying microbially induced carbonate precipitation discovered that certain bacteria can produce calcium carbonate crystals that bind sand particles together. In large experiments, researchers injected these bacteria into sand and created solid structures with strengths reaching 12 megapascals, comparable to some architectural concrete, grown entirely by living organisms at normal temperatures without industrial emissions. Both discoveries reveal the same fundamental principle. Nature already knows how to turn loose sand into solid stone. Coral reefs, shellfish, and natural limestone formations have been doing it for millions of years. The challenge for engineers has simply been learning how to accelerate that natural process on a human timescale. Recent research suggests that with a small amount of electricity or the help of microorganisms, sand can transform into rock in hours or days rather than over geological ages.